Okay, so it's 9 o'clock. Good morning, all strong people in this early morning session. It's Thursday, the third day of virtual conference Open Readings. I would like to welcome all participants, young researchers and colleagues. My name is Mažena Mackoit-Sinkevičienė, and I am one of the local FTMC scientists from Department of Optoelectronics. And it's my huge pleasure to introduce today our keynote speaker, Tomas Tamulevičius, representing the birth town of Hermann Minkowski, one of the greatest teachers of Albert Einstein. And currently, thanks to Tomas Tamulevičius' research group, Kaunas is emitting new, strong photonics vibes too. So Thomas is a young researcher, but it would be difficult to believe so looking at his extensive portfolio of publications, of textbooks and awards. He received his PhD in 2012 in Kaunas University of Technology, and during his scientific journey, he studied even in France. He had an internship at IBM Research in Zurich, Switzerland, and currently he is a chief researcher at Institute of Material Science of Kaunas University of Technology and professor at Physics Department of Kaunas University of Technology. I think that probably it is worth mentioning that in 2019, together with his colleagues, he received Lithuanian Science Award, which is issued by Lithuanian Academy of Sciences, for the work cycle, which was dedicated to nanostructured materials for sensors, for photonics, and for energy generation. Moreover, since 2020, Thomas is a member of the Young Academy of Lithuanian Academy of Sciences. He has been active in various fields and outreach activities, and among all this, despite all those projects, he still has found a time to establish his spin-off company, Holtida, yes, that produces holographic security labels. And I think last year or two, together with a team from Lithuania, Latvia, and Japan, he came up with the method that forces over 300 million nanoparticles, metal nanoparticles, yes, to self-assemble into desired regular structures. So I'm really looking forward to the lecture on those self-assembling nanophotonics. And Tommy, the floor is yours.
Yeah, thank you very much. I'm touched by the introduction. Really, thanks. Thank you very much for invitation. Just starting my presentation. It's really fun to be part of your nice conference. And today, as it was introduced by Mažena, I would like to speak about self-assembled nanophotonics. And just a few words why this conference is important for me, because it was my first poster presentation in Open Readings back in 2006. I was a fourth-year bachelor student, and I am very proud of myself standing next to my poster here. And it was quite some time ago. It was about optical characterization of microstructures, and my co-authors was my future PhD supervisor, Dr. Mindaugas, my current colleague, Asta Gobiene, and a PhD student, Giedrius. He's still, they're all working in our university at the moment. And during a very, only 1 year later, there was this nice scientific American paper, The Promise of Plasmonics, and many people were started to be enrolled in this field more actively, and many of them later on showed some images from this paper as a motivation to work in this field. So I'm just telling that maybe I was at the right place, and it was the right time to attend this conference. So I would like to say a few words where I come from, because it's an international conference, and maybe not everyone are aware of our university, but only a few slides. Then I would like to introduce a few words about this local surface plasmon resonance and why it is important. I hope that won't be too much of this introduction. And then switch to ways to fabricate nanostructures, and that's the place where we probably did our biggest efforts and got most interesting results. And at the very end, if I have some time, I will introduce a little bit another topic: what can be done if those particles are not that much ordered, but still plasmonic, so they're like random distributed. And those applications will be the surface lattice resonance, which I will try to explain for you. And that very last application, the absorbing coatings, the project that I'm currently leading. And I will close my presentation speaking about the startups, and you will see that actually now we have a second one. So after such a informative presentation by the chair, I'm not sure if I have much to say, but I graduated Kaunas University of Technology in 2012, got my PhD, and I also spent some time abroad studying at University of Southern Denmark. I had a longer internship at IBM, and there was also some visits in France and Japan. And currently, I'm a professor at Faculty of Mathematics and Natural Sciences, where we have a research group, Applied Optics and Photonics, where I'm the principal investigator. And also, most of the time, I stay at the Institute of Material Science, where I'm a chief researcher. And yeah, thanks for noticing about Lithuanian Academy of Sciences. So from last year, I became a member of Young Academy, and also a co-founder of Holtida, which is between the sponsors of this conference. So I will allow myself to show one slide about Holtida as well. And we recently established a company, Nanoversa, that is very much related to what I'm going to speak today. So I will also spend one slide on that as well. And we have also an Optical Society of America student chapter in Kaunas. And I'm the faculty advisor of this student chapter. And I saw that some of our student chapter members are listening to the presentation as well. So very brief about our university. So we have like close to 10,000 students. I think we are not reaching this 10,000 yet. And around 1,000 academic staff. And if you are not aware about Kaunas history, so we were a capital for a very short time, and we are willing to become a capital again in 2022, and it will be cultural capital of Europe. So if you are interested visiting Kaunas, maybe year 2022 might be a better choice than this year with these lockdowns. This is our campus, and this is our Santaca Valley. Our institute is also located here, and mathematics and natural science faculty is located in these buildings. So we have like 8 research institutes, 2 valleys, one of them you see here. and 4 campuses in 3 cities. I would prefer having 1 campus, but yeah, it's getting better. And we have nine faculties. And the Institute of Material Science was founded not so many years ago in 1994, and it mostly focuses on the micro and nanotechnologies and has some special topic of optical document security, this field that is very much related to the whole TIDA that was mentioned already. And I think this is one of my last slides about university. So we have some facilities in our institute, in our university, and we are part of Open Research and Development Lithuania Open Access Center. So these tools and hardware is accessible for everyone. And we have some analytical tools and technological equipment. And the things that I will mention today will be probably transient absorption spectrometer, femtosecond laser micromachining system. But some of the work is also done in the clean room using, let's say, electron beam lithography or reactive ion etching and plasma etching. But I won't go into these technical details. If you are interested, you can find those in the publications. So coming now to the topic of the lecture today, and this localized surface plasmon resonance. I'm sure that 90% of you have heard of it, but it's a wide audience in this conference as possible. So I let myself speak a little bit about the basics as well. So I took some phrases from the Stefan Alexander Meyer textbook, Plasmonics, Fundamentals and Applications, and he's recognized like with a golden standard to learn about it. So what are those LSPRs? So we have non-propagating excitations of conduction electrons in metallic nanostructures coupled to electromagnetic field, and it's what is shown here at the bottom. We have electromagnetic wave coming from the left to the right, and we have metal nanoparticles that are of different size. And already in this cartoon here, there is some differences between bigger and smaller structures. And in principle, what these pluses and minuses show is that the charges are willing to redistribute in this confined space following the electromagnetic field orientation, and the electromagnetic field is toward down here, and we have the charges opposite. And when this wave is traveling, they are going up and down. But if we have a particle that size matches to, let's say this, it's a bit of a naive representation, but we could think that Bowl wave fits into the particle, so then we would kind of have those pluses and minuses in a more complicated fashion distributed, and then we can have dipoles and quadrupole resonances. So don't trust this animation too much, because this theory works well when those particles are much smaller than the wavelengths, and here I would say it's too close in this cartoon to the size and the wavelengths. And what happens with these particles when we have those localized surface plasmons excited? So they scatter the light in a very characteristic way, and those nanoparticles, they are willing to restore these charge separation and drive those electron oscillations. Can this happen in any material? No, and actually it matters what you choose. And here the most important factor is the dielectric constant and the dependence on wavelengths. The dispersion curve of the dielectric constant plays a big role. And in the seminal paper of Johnson and Christie that I checked was cited on the weekend, I checked, it was cited more than 12,000 times. those two authors announced what are the dielectric constants of gold, silver, and copper. And on the top we have imaginary part, and at the bottom the real part of the dielectric constants. And actually, this part of energy could be addressed to the visible part of the spectrum. And we have some transitions here that are called the interband transitions, and therefore the gold has a yellowish color, and the copper looks reddish, while silver has this metallic look because its interband transition is not in the visible spectrum. So the dielectric constant, the real and imaginary part are written like that, and the overall is this complex dielectric function that is important for us. But gold, silver, and copper is not the end of the story. There are many more materials, and there is also aluminum that is very much investigated now, and there's some materials like titanium nitride and some others that are also playing this effect is also working on them. What is also important is where we put our nanoparticles. So before I was just saying that they have to be small, but it is very important where we place them. So the surrounding or the medium around them. And the scattering and absorption cross-section of those nanoparticles sum up and adds into the extinction. So that is the light that is lost when it interacts with those nanoparticles. And I don't want to go into details with those equations, but it is important to take notice at the denominator, where we have epsilon of metal plus 2 epsilon of medium. So medium is around the nanoparticle. And yeah, this alpha is the polarizability, which also has the same structure here. And there is a condition called the Froelich condition that describes the dipole moment in a sphere when it is present, at which conditions. And it turns out that when this denominator is equal to 0, we have a resonance. And here is an example from the same textbook I already mentioned, that for a silver sphere, in here we have the resonance at one position, and when it is in silica, in some kind of a glass, we have a position at a different energy. What also matters is the size of the nanostructures that we are dealing with. And if we have a smaller ones, so because of those equations I showed you, the absorption dominates, and it scales with the radius by a power of 3. And when the size increases, so the position of the resonance redshifts, and then the scattering starts to dominate, because this is overcome by the radius by the power of 6. So in small nanoparticles, we have big restoring force of those charges, and in bigger particles, this restoring force becomes smaller, and we experience broadening of the resonance. And here are some numerical simulations with this knee theory for silver, gold, and copper. You will see why, because we had some small project about it. And if we are increasing the size of the sphere, you can see that the dipole peak is shifting to the longer wavelengths, and it's really broadening, as I just said. And for gold, it is in a different position. The resonance, you can notice that is in a different position because it has a different dielectric function. And for copper as well, it's slightly shifted, and copper has not that well expressed peaks because it has a little bit different structure. And here is a bit more sophisticated numerical example I borrowed from some publication, where we have a silver sphere of diameter of 62 nanometers and some volume here. And you can see this blue or truncated yellow line, which represents scattering by this sphere. And you have absorption here at the bottom with the two peaks. And those two peaks, they are shown here as the surface charge distributions. So at this peak A, we have a dipole, and at this peak B, we have a quadrupole. So that is the same thing that I was showing at the very beginning when I was started speaking about localized surface plasmons. Is the sphere the end? No, it's not, definitely not. So the shape matters a lot. And there are many nanostructures that people have researched recently. And one of the interesting kind of them is polyhedrons. They also have a special name, platonic solids, a set of them. So there is a nice paper that I'm borrowing some illustrations from that is showing the extinction cross-section depending on the nanoparticle shape of this plasmonic material. And we are shifting from sphere to dodecahedron, and then isohedron and hexahedron, which is actually the cube, and the octahedron and tetrahedron. Very hard names for me to tell. And to be honest, when I see these nanoparticles through the scanning electron microscope, I'm always never sure which shape they are. And we have some expert in Japan, I will introduce him as well, helps us to discriminate which ones. But maybe you have also heard that we can have nanorods, and then we have long nanoparticles. So we might have two resonances, longitudinal and transverse. So then we have two peaks. And this is a little bit easier to understand maybe with this, also this slightly simplified cartoon here, why we have two resonances. And it's a bit more complicated to understand why we have more resonances here. But we should have a look at these charge distributions and so on. And then it appears the reasoning comes into mind. What is also interesting is that you can make not only nanorods, but you can make much more complex structures like bipyramids or even some kind of dumbbells, and they have even more interesting properties. Now, I was speaking about separate nanoparticles or maybe suspended in the colloid, but what happens if we order them? And that's actually the topic of my presentation. So order is very important. And many years back, Wood announced a paper on a remarkable case of uneven distribution of light in a diffraction grating spectrum. And he noticed that by changing the angle of incidence in observing the reflectance, you have some dips, and they follow some trend. And that is what we usually call now the Raylight anomalies. And if we put this together with the broad absorption band of the surface plasmon resonance in the nanoparticle, and place those nanoparticles in the special fashion, so we have a tremendous narrowing of the LSPR peak, and we can get like 1 to 2 nanometer sharp so-called surface lattice resonance peaks, and that was what we're investigating in our work. So it works with the dielectric gratings as well, and we had some sinusoidal and rectangular structures. But it's more interesting when you have them in a 2D, not in a line, but in a 2D. And then you can call this metasurface. And I guess you have heard about those as well. And there's some nice illustration from Science cover magazine and some artistic representation of a lens that is made from a metasurface. Yeah, of course, I'm borrowing those illustrations. That's not my science paper. I still don't have one. I hope I will someday. So the optical metasurfaces is the 2D analog of the metal-based metamaterial. So it's like one slice of the metamaterial. And I borrowed some sentences here from a nice review paper. And it's an artificial nanostructured interface that has sub-wavelength thickness. So it's important to have very thin layer. And it manipulates light by specially arranged meta-atoms. And those meta-atoms could be nanoparticles. And it actually doesn't have to be metal nanoparticles. It could be also dielectric nanoantennas. And they are influencing on the optical properties of light that is interacting with such structures. So how to make those? And of course, we have this top-down and bottom-up approaches to make any kind of a nanoscale objects. And with this top-down, you go to the clean room, you use some lithography, and you end up with a structure of demand, something that you want. And there is some analysis made here in this paper I borrowed again. And the size deviation is like 21% here. I guess they use quite a good lithography tool. And if they make smaller structures, this deviation is like 14% or so. But really, if you look at it, you see that it's not that high quality. And each of this sphere is slightly different and has some roughness and so on. So why not to use something that happens itself, some bottom-up approach? So you need to have a fume hood, not the clean room then. Yeah, don't try to do it like I show you here in the example. And then you have to do some chemistry and synthesize the nanoparticles that you like. And then if you have some template, then you can order them. And then it ends up into something that looks really similar. And this is the TM images of the chemistry of the wet chemistry synthesized nanoparticles, and their size distribution is like 15% of this particular example here. So it's like in between here, but it looks much better when you look with the TM, and it promises some good optical properties as well. So how to gain the most from those nanoparticles and the self-assembly? So why not to use the best of two worlds? Use this collective assembly, which forms layers from small particles, which is known, and apply a bit of lithography to define the positions that we want our nanoparticles to sit in. So we can arrange some nano templates, and in this case is like 600 nanometers, let's say. And what we expect is that the nanoparticles will sit into those pits like the eggs here in the box. And the Easter is coming, so this technology is approved by the Easter Bunny. And there's also a saying, don't put all your eggs in one basket. So in this case, we are the opposite. We want to put all our eggs in those baskets, and only then our metasurface starts to work. So how to do it? How to make this experiment? So there is this technology termed capillary-assisted particle assembly, according to Heiko Wolf in IBM Research Zurich. And you need to have a stable colloid of your micro nanoparticles. It works for different sizes. You have to define the nice template that has the traps that the nanoparticles can fit in. You need to have a translation stage that is can ensure slow translation. You need to control the temperature. You need to have some cover slip confining your drop. And it's good to have a microscope that you can investigate the process. So what happens? The liquid dries out, it evaporates, and those particles, they are trapped by the capillary force in the obstacles that you have designed in your template. And in such a way, you can cover big areas with nanoparticles with 100% yield. And here is a nano movie made by a director, Dr. Mindaugas Hedėnas from our team. And this nano movie, you can see like this substrate is slowly translated by some micrometer or below per second. And we have these V-shaped obstacles that are able to trap in this case, polystyrene beads, because you can see them through the microscope. So this is the microscope, this is the translation stage, and the process happening in here. So the cameraman is on top in this case. So we did some research with polystyrene spheres that are fluorescent because it's easy to see them. And we did some investigation on what happens when we have a trap that fits one particle and the trap that fits many particles, and did those deposits under slightly different conditions. And you can play with the speed and with the temperature. And also you have to take into account what is the humidity in your lab, because you have to control what is the dew point in your experiments. And then we did the analysis of those images, like took many lines through the image and analyzed them automatically with some code, and calculated the yield of this deposition. And we found that we can control the transition from like poor deposition to 100% yield. This switch in this transition by selecting the good conditions of the speed and the temperature. We use some sigmoidal functions to describe it. And this is the case of a single particle per trap. This is the case of a multiple particle per trap. But there is some kind of a space, like around 40 micrometers, that is not of a good quality when you start to deposit. So you're willing to make it as small as possible and not to like have half of your sample partially filled. And it looks like this. So let's say if you are willing to work with a single particle per trap, maybe it's worth to go lower in velocity and lower in temperature. And when you have multiple particles per trap, design template, so maybe then it's worth to go faster and at higher temperatures. So you have to play around and find the conditions, but when you find it, it's like 100% yield. The drop is tending to dry out, and you lose your nanoparticles. So the idea came from our colleagues again in IBM Research Zurich, that you can apply microfluidic device to supply this liquid while you're doing the process, because then you cannot not only supply the single liquid, but you can have multiple ports, and you can do, let's say, gradients, like shown here. At the beginning, you have red particles, and at the end, you have mostly blue particles, and in between, you have some kind of a gradient. Or you can do multiple deposits by letting the liquid in, making the assembly, taking what's left out, putting another liquid in, and making another assembly. And in such a way, you can start thinking about some complex platform that is good for making nanostructures on what you have planned. Now I would like to switch a little bit more on the nanoscale. So it is very nice that we have had this collaboration with Dr. Joel Henze. I borrowed his slide here from NIMS in Japan. And he's very good at synthesizing well-defined nanocubes. And by doing this chemical reaction, you can control the size of the cube by controlling the length of your reaction. But the cubes are not the end. You can have more complicated structures that I presented you previously, all those octahedrons and cuboctahedrons and so on. If you control your reactions well, and you can also have some nanorods and plates and so on. And those nanoparticles, they have very interesting scattering properties depending on their size and shape. And here is an example how they look. So when they are growing, they transform from cubes to truncated cubes to cuboctahedra and octahedra and so on. They scatter light at the different wavelengths because they are of different size and they have different resonances. What you could also do, you can make even opposite structures if you are using galvanic replacement. and do some nano cages. But I'm not going to speak about that. If you're interested, you can follow what Yonan here group is doing. And there is also alternative for the chemistry. You can use a femtosecond laser to ablate the target, and we use this ytterbium KGV laser from light conversion to make silver, gold, and copper colloids. So you simply scan the beam at the good energy and translation ratios, and you can see how this colloid is appearing. So there are many ways to make the nanoparticles, and different ways are good for different applications. And if you are interested in this, you could visit the poster by our bachelor student, Gerda. It's probably already presented, but I think they are still online. We also had an idea that we can combine nanoparticles, or plasmonic nanoparticles, with some interfaces with TiO2. And this material is good, is known as good for synthesizing for missing the word. Good for cleaning the water and inducing catalysis, but it works only well for the UV part of the spectrum, and we know that the sun is shining a broad spectrum, and the metallic nanostructures here can play a role because they can absorb light in the visible, and having this charge separation and transfer to TiO2, we can synthesize this reaction here. And together with our colleagues, we have investigated nanoparticles that are like a core shell structures with titania. So you have to do some advanced chemistry to synthesize those, but you can coat and see that this coating is not destroying the plasmonic resonance, and it's according to the simulations. And what is interesting with those nanoparticles, I just want to spend one minute here to explain that what happens when you excite nanoparticles with femtosecond pulses. So they absorb the light, we have some dephasing of electrons, and then we have electron-electron scattering, and those are very fast processes and hard to catch if you have a pulse that is longer than 100 femtoseconds. But then those electrons, they start to release their energy by sharing it with the phonon. So we have electron-phonon scattering, and that heats up the nanoparticle. The nanoparticle expands. It still has the same number of electrons inside, so the energy density of the electrons changes. And when it expands, it is willing to contract again, and it starts to work as a spring. And if we have cubes, like in our case, and you have this localized surface plasmon resonance, so this oscillation means that this LSPR position should be oscillating together with this oscillating nanoparticle. And we have some complicated optomechanical modes that are induced by the femtosecond laser, and they look like this for a certain size of a nanoparticle. So this is this tip mode, and this is this face mode, and how to follow these things optically. So here the transient absorption spectroscopy stands in, and I don't have time to introduce this method well, but in principle, it is an absorption spectrometer that is capable to measure many times in time when we delay the excitation pulse, and we probe the sample with the white light that we get from the white light supercontinuum. For the excitation, we need to have a laser that is pumping the collinear optical parametric amplifier, and for the white light, we can use this supercontinuum. And yeah, this system is from light conversion we are using, and really, if you have questions about it, they should be addressed to Professor Mikas Vengris. I saw he had a presentation maybe 5 years ago in your conference. It's still on YouTube, so you can have a look at it. And I'm very glad that they are progressing, the company is progressing, and the setup we have is, it works well, but this one is even more fascinating and good looking. So yeah, you can follow them on light conversion webpage to progress in this field. But I'm coming back to the examples. So how the cube oscillation look when you measure the spectrum. So you can see those oscillations blinking on and off, on and off. And it's very nice to describe with the optomechanical oscillation that is characterized by damped harmonic oscillation function. So very simple mechanical solution from that. And it scales with dimension, and you can see the shift in position if you have this titania, because the resonance shifts at a different side of the spectrum. And it has a linear dependence of this period on the edge length and the Q factor, the quality of this oscillation, and on the damping time that is used to fit those equations. Maybe I will skip this because I'm a bit running out of time. And what we noticed is that if we have this titania of a different thickness on those core shell structures, so we have different decays and slightly different amplitude of those oscillations. So we think that there is some energy transfer between the electrons in this plasmonic nanostructure and this TiO2 we have on top. Okay, so I'm now coming to this surface lattice resonance. So what if we arrange those nanoparticles that I was just speaking before? So we take the same nanocubes, we apply this method of assembly. Those nanocubes are very nicely monodispersed. And here we have different lattices of the templates with a pitch of 300, 350, and 400, and in this case 600 nanometers, and it's hexagonal, not a square one. And you can see that we have different color, and we did some measurements, and they appeared very interesting optical effects that are easy to explain. And not only the distance between particle influences, but number of particles per trap influences. So by controlling the number of particles per trap, you can also switch from, let's say, bluish to reddish color as well. So here, I would like to summarize a bit. If we put those nanoparticles that has this localized surface plasmon resonance into a grating that is designed that the ray light anomaly, which I introduced, is on the left side for this plasmon resonance. So we can get the narrowing that is called the surface lattice resonance, these sharp dips. And if we make the angular measurements and transform those angular measurements into this K-space diagrams, so we can see that our peaks that we are observing are nicely following the trends that are expected from this photonics, from this regular fashion of those structures. And they can be explained by this coupled dipole approximation when it's orthogonal illumination. And when it's inclined, it's a bit harder to predict, but we managed to use this finite element modeling to show that our peaks that are very high quality, at least for our research, reaching like 80 or 60, could be easily explained at different orientations. And what we also observed is that you can expect that if nanoparticle is oscillating, so you are changing the plasmon resonance condition, and this SLR, which is related to this plasmon resonance, should also shift. And what we observed that it's really shifting as well. So that was a very nice work by Mindaugas. He just defended his thesis recently, where we showed that we can follow this SLR in the transient absorption spectroscopy. So we can like manipulate this very narrow line in time, and we see that there is some nice applications for that in the future. So there's some outlook for these SLRs. So one of the outlooks is application is nanolasers. Everyone, I guess, knows in this audience, I don't have to introduce how laser works, but they are quite big. And there was this Nobel Prize in 1964. But what people are doing now, they're trying to make everything smaller, and not like 2 times smaller, but by orders of magnitude smaller. And there was some progress making the laser smaller as well. And the very recent progress is that people use lattices of plasmonic nanoparticles, where we have this SLR resonance, which works as a resonator of the laser. And you have to apply some dye molecules that work as the active medium. And then you need a femtosecond laser to pump. And there is some work by other group, by Terry Odom, where they showed that you have this typical lasing behavior. The other application for the SLRs is nanosensors, and they could be very sensitive to some molecule bindings on those cubes, because they might shift the resonance and the mechanical properties. And also, there is a very nice application of SLR enhanced surge sensors. So you can enhance the Raman signal by having a resonance excitement from the nanoparticles. And I don't have time to speak about this, unfortunately, but we just recently got a project from mRNet where we will work on those directions. So here I would like to advertise a bit this new startup company, Nanoversa. So our idea is that we can provide silicon masters of your application. We can also make elastomer templates or provide the materials that you need to make those. And if you don't have the colloids, so we can provide the colloids for you. We also have a prototype of the machine that is capable to run this process in your lab. And then you can get your SLR for your application, or you can tell us what you need and we can provide you with those SLRs just prepared for you. And they also work with these resonance enhanced Raman scattering sensors. And we are also doing some diffractive optics if you need, because it is the same technologies like making the silicon masters actually. And this project is financed by MITA, I should mention. And if you are interested, there is some work that's very much related by PhD student Najea, P239. You can join that. I see that my time is almost out, so I will try to be very, very short here. So it doesn't have to be regular in order to have interesting optical effects. And here is wet chemistry synthesized nanoparticles. And on the right side, we have deposited, thin film deposited nanocomposites. And how we do that, we use magnetron sputtering, and we have a metal source of noble metal, silver, and it happens in carbon atmosphere, hydrocarbon atmosphere, and we can grow thin films that have metal nanoparticles embedded in the so-called diamond-like carbon, which is a nice dielectric transparent material that is also hard. And it has many applications, not only to photonics, because those nanoparticles in such a films, they show piezoresistive properties, they show antimicrobial properties, they have very nice LSPR properties, and this could be used for absorbing films, and it is the project that we are currently running, financed by European Space Agency. I just wanted to say that if you are interested in nanocomposite films, and I didn't have time to speak about it today, we have a nice review paper and reports of progress in physics, so you can follow that. Just one slide about the progress in our reports. Very recent work, just submitting our milestone 2 progress report last week. So we have those nanoparticles that are of a small size, and those films are hard and black at the same time. And we can predict, and we can get the results that give this broadband absorption, and those films look black even under high angles of incidence. So it's not simple interference like in the dielectric mirrors you have. And there are multiple posters about this topic. So if you are interested, you can follow Paulius, Aušrinė, or Julia on the different aspects of this topic. So I'm closing here almost my presentation with a small advertisement about Holtida, as we are a hologram sponsor of the conference. Unfortunately, in virtual conferences, you are probably not having certificates, but if you will have them some year later, maybe, or if you have them from last year, it might be that the stickers were produced by Holtida, which is a member of Lithuanian Laser Association. And we have some design software or holograms. We have origination techniques, multiple ways to do the originals of the holograms. We can produce nickel shims, and we can do label production, like roll-to-roll printing. It doesn't have to be stickers. It could be on the coins, like it's done together with the Lithuanian Mint Factory. And if you're interested, just contact us through our webpage. So here I'm finishing up, and we had some financing, of course, that is very important. We had some cooperation with companies that helps us with our laser setup and with ideas, and some companies that are currently working with us on the project. And there is most of our team, it's not all our team, most of it. And the image was taken 2 years ago during the summer practice. And there's some poster numbers of people that I didn't mention in my presentation, but they're also working in our research group. And there's some people that are giving insights for us, and those two contributed most this time, like Joel Hensig with the nanoparticle, and Vladimir Bordeaux helps us with this very last topic I showed you. And with this, I would like to stop my presentation and only mention that we are also planning to organize a school again, Advanced Materials and Technologies. It is usually happening in Palanga, and I think we are considering now to make it a semi-virtual, semi-real conference. And we will see how it goes. But if you're interested, so follow the news in our webpage. So thank you very much for your time and listening, and I'm open for questions.
Okay, thank you very much. I'm sure that everybody enjoyed this inspiring talk. Thank you very much for this interesting and enjoyable lecture. I think, yes, now we are open for some questions, but perhaps I shall begin with some as a chair. So for me, it is interesting to know about those nanoparticles' structural sensitivity. Have you investigated, for example, the effect of environment on the spectrum in terms of stability? For example, after 1 month or so, is it stable?
So those wet chemistry synthesized nanoparticles, they're really stable. We have them in the shelf for even several years, and they still have nice properties. They are kept in alcohol, so it's not oxidizing, and they are very good crystalline quality, single crystalline nanoparticles, and they're very stable. I wouldn't say that about those laser-made nanoparticles, let's say a special of copper, which is oxidizing in days. But with gold, it's stable as well.
Okay, thank you. You have mentioned different type of techniques, like top-down nanofabrication procedure, yes, and this SAPA, capillary force assisted. Yeah. So what is the biggest advantage of this CAPA, let's say? Yeah. And does it depend on particle size, composition?
So the biggest advantage here is that you take the perfect ideal nanoparticles that they, like, with the help of nature, they are designed, and you put them in the positions that are lithography quality defined. So you gain like two things at once. You have very well positioned and they are of a much better quality. And you don't have to run each time to the clean room to make a new structure. You need to make it once to make your template, and you can replicate those templates many times.
Okay, definitely it sounds like a better choice. Are you going to create even more complex 3D structures than those mentioned, cubo, octahedra, or something?
So I think that for different applications, we need different nanoparticles. And let's say if you are interested in the resonances at the higher frequency, then you have to switch to bigger particles. And sometimes they are transforming from cubes to some cubo-octahedrons without, we cannot influence this because after a certain size, those cubes, they translate their shape. So we no longer can preserve them. So it's application demanding, and also there's some limitations in the chemistry.
Okay. One question additionally, if we want, for example, to generate with stronger surface lattice plasmon resonance, is it better to use taller or smaller nanoparticles?
So it is important. It is important to have the correct arrangement, the correct position of the plasmon. The nanoparticles should be all of the even size. And we found out that in principle, it works well when they are on top of the surface, when they are embedded into this template, when they are sitting inside. And this size, I think it's very much related to the resonances that you need to have.
Okay, so are there any plans to actually develop those mentioned ultra small nanolasers? How about, for example, development of implantable nanolasers for medical applications, in Lithuania?
Yeah, so what I can tell you is that Mindaugas Jodėnas already made experiments in the lab. I also saw myself that nanolaser shining. It's not published yet,
Wow.
but we have this project just started, so we are planning to work on this direction, and I'm still not sure about the applications of those nanolasers, but really you don't need much. You need only to have a die on top of that meta surface, which is just a piece of a glass with the pits and the nanoparticles on it. And you have to bring the femtosecond light to it. And this fluorescence of the dye could be of different color, and you can control the resonator by changing the arrangement of nanoparticles. So there's many freedom here.
Okay, maybe one of not so good questions, but sometimes people observe quenching of photoluminescence. Have you observed that or fighting it?
Yeah, I would say it's a bit too early to say at the moment. We haven't researched much in this field, and I'm really looking forward to it because I'm buying optomechanical elements for a while, and we still don't have time to sit to this interesting research that is waiting for us. I think this spring.
You're still ahead of that. Okay, it sounds really promising. Let's take a look. So we have about 100 people if we are summing those in Zoom and those in YouTube. So let's take a look. Have we the questions? Okay, so people are not brave enough to write them down. Let's
hope too early.
Yeah, it's still early, just 10 o'clock. So all of you who wants to ask something, but it's not brave enough, you can write for Thomas. I'm sure that he will answer. I would like all of us to thank once again for our keynote lecturer, Tomas Tamulevičius, for this inspiring lecture about this world of nanoparticles. And now I just will remind that student session starts in 15 minutes, and just have a great conference, and let's meet maybe in Palanga in this summer school.
Yes, sure.
Okay,
thank you very much for the invitation again. Bye.
Bye.